Hello everyone, my name is Wouter Raateland from the TU Delft, and in this talk I'll present to you a novel method for performing large-scale fluid simulations with high performance. So, in interactive simulations of fluids we are confronted with conflicting goals. On the one hand, simulations need to be fast in order to enable interesting and exciting interactions. On the other hand, simulations need to be accurate and of high resolution in order to be intriguing and meaningful. So the problem with high resolution simulations is simply that they lead to complex and high dimensional computations, which in turn place high demands on the performance of simulation frameworks. However, fluid simulations do not require a highly resolved grid everywhere in the fluid domain. Some parts of the domain may be empty, or they can be adequately represented by a lower resolution grid. So, to capitalize on these varying resolution requirements, we can use adaptive grids and thereby decrease the number of cells that are required in total. So, these adaptive grids can either be sparse, high resolution grids, such as GVDB, or on the other hand, they can be hierarchical multigrids, such as SPGrid. Compared to uniform grids, spatially adaptive grids are a bit more complex in structure, and therefore the cost per cell is a bit higher. The most common operations in fluid simulations can be implemented based upon random and stencil access. So, while random access and stencil access are easy and fast to perform on a regular grid, they can be more complex on adaptive grid structures. To achieve high performance simulations on adaptive grids, these operations need to be supported with minimal overhead. In our work, we represent two main contributions. The first is dynamic constraint grid, or DCGrid, a novel multi-grid data structure. The second is a local topology adaptation algorithm that optimizes the grid topology based on the simulation state. So, DCGrid is a GPU-based data structure, and it models a multi-grid using a hierarchy of sparse uniform grids. And the sparsity of each of these grids can be adapted dynamically during simulations. So, for cache coherency, DCGrid stores the data for each uniform grid in blocks. And the location of these blocks is linked to their location in memory using a hash table. And if we zoom in a bit, we see that each block consists of 2 by 2 by 2 subblocks, and in turn these subblocks again consist of 2 by 2 by 2 cells. So the data for the blocks, subblocks and the cells is stored in 3 separate but equally ordered memory spans, and the cells in each block are ordered via a Morton encoding or a Z-filling curve. Together, this makes it very easy to find memory locations of cells given the memory locations for blocks. To efficiently perform stencil access in DCGrid, we restrict the grid layout of each of the grids in the hierarchy such that the area spanned by a fine grid, here on the left, is always a subset of the area spanned by the coarser grids. This does introduce some redundant low-resolution cells. However, as the resolution between each level of the hierarchy differs by a factor of 2, at most 1 out of 8 cells can be covered by another cell in any configuration. We also pre-compute the indices of the cells directly adjacent to each block in a structure called apron cell indices. This apron of cell indices uses lower resolution cells when the higher resolution cells are not available. So, in summary, to perform random access in DCGrid, we perform a hash table lookup to find the location of the block in memory. Then, we apply a simple linear transformation to get the cell index from the block index. To perform a stencil access, we perform a random access at first to get the location of the center cell. Then we look up the indices of its neighboring cells in the apron cell indices data structure. We benchmark the performance of DCGrid against the other state-of-the-art adaptive grid structures SP-Grid and GVDB on an equal sparse domain, and on both a stencil and a serial kernel. DCGrid consistently performed faster than both SP-Grid and GVDB on all the resolutions that we tested. Now that we have our adaptive grid structure and the basic methods for running fluid simulations on it, the next step is to adapt the grid topology to the simulations. And in other works, several methods have been used here. Some works have used static resolution distributions, for example, based on the proximity of a cell to a solid interface. Other works have hard-coded the resolution per time step, and they just copied the data and the topology from one time step to the next. Other approaches used methods based on thresholds and subdivision, and yet others took an optimization-based approach. Well, we introduced an efficient optimization-based algorithm for adapting the grid resolution over the spatial domain. Our algorithm optimizes the grid topology under a memory constraint, and the optimization criterion can be configured by the end user. Our algorithm works by assigning a priority score to each cell. In our experiments, we used a cell's vorticity magnitude as its priority score, but it's entirely possible to use any other measure, such as a cell's velocity gradient or perhaps its distance to the camera. Our optimization criterion is now as follows. We want cells with higher priority scores to have a higher resolution. However, we can only assign a maximum number of blocks on each of the grids in the grid hierarchy. And our algorithm approaches this optimization criterion in two phases. First, there's the initialization phase. Here, we allocate the cells on the grids for which the block limit is sufficiently high such that they can be densely allocated. And then we repeat the following. We simulate a single time step, and then we calculate the priority scores per subblock as the average of the priority scores of the cells contained in these subblocks. Then we refine the subblocks with the highest priority scores. Of course, we respect the block limits here. And we repeat these steps until all cells on the finest resolution are allocated. So, as the simulation progresses, the distribution of high priority cells will shift around, and that's where the second phase of our topology adaptation algorithm comes in. The second phase adapts the grid topology to account for these shifts in the following way. So after each simulation step, we consider each pair of grids adjacent in the grid hierarchy. And for each pair, we compute the priority scores of the high resolution blocks and of the low resolution subblocks. And we then find pairs of blocks and subblocks where the priority score of the high resolution block is lower than the priority score of the low resolution subblock. These pairs violate our optimization criterion. To solve these violations, we coarsen the low priority blocks and refine the high priority subblocks by moving the low priority blocks to the location of the high priority subblocks. And here we see DCGrid and our adaptation algorithm in action. The DCGrid simulation uses only half as many cells as the uniform simulation. Still, the result is of similar quality. When we use a lower cell limit, we see a similar result. However, the resulting quality is visibly lower. As a practical application, we integrated DCGrid with a simulation of weatherscapes, and we reproduced the scene in which many different types of clouds form, from fog on the left to cumulus clouds on the right. And to do this, we designed a new interaction scheme between the terrain and the atmosphere that supports cells of different sizes. And with this new interaction scheme, we were able to simulate phenomena that require rapidly changing values at the terrain, such as this wildfire that we see here. So, in conclusion, we introduced DCGrid, a novel GPU-based multi-grid data structure suited for efficient fluid simulation that outperforms the state of the art. And we introduced an efficient and optimization-based topology adaptation algorithm on DCGrid that is user configurable. DCGrid is currently limited by two factors which could be addressed in future work. First, there is the fixed block size of 4x4x4 cells. Allowing users to vary the block size could be beneficial to some simulations. Secondly, we use block limits per grid in the hierarchy instead of only one global block limit. Using a global block limit would allow for more flexible grid layouts, which could help in highly dynamic scenarios. And by that, I'd like to conclude this talk. Thank you all for listening, and I'd like to welcome any questions you might have.